Thank you, and good afternoon. So, firstly, I would like to thank the organizers for this invitation and also the opportunity to present my work in front of this audience. Today I'm going to tell you a recent work on what I have titled Beyond-Dirac fermions, and my meaning will get clearer as we go along. And for this, uh, the property of three-band nature of my construction will be important, and also a graphene-like property will be important. And this is in a toy model spirit, just to understand some geometry of wave functions. So this work has been done in collaboration with Ankur Das, who is a graduate student at University of Kentucky, and he's also there in the audience. So here's the outline of my talk. So my motivation is really a toy model building motivation. And you can think of it as also band engineering, which is also people are thinking about it actively in, thinking about it actively in different platforms. And to set the stage, I will quickly review the SU2 nature of regular two-fold Dirac fermions with two bands. And then, having set the stage, I will come to this main three-band Hamiltonian that is of interest to me. And I'll show how this is going beyond Dirac. So I'll give a winding number way of understanding the geometry of these wave functions, and then a symmetry perspective similar to Dirac fermions, the two-fold Dirac fermions that we do in regular graphene. And this model can be put on a lattice, and this is the diagram of the lattice. It's a hexagonal lattice with 3 sites per unit cell. And this is mainly the content of our paper, but I'll spend a little bit of time to discuss its relevance to 3D, where perhaps the ideas in this talk will be most directly relevant. And if time permits, I'll conclude with a geometric phase type. Okay, so as far as motivation goes, so of course, as in many talks we have seen that the geometry of some parametrically dependent wave functions is very interesting in condensed matter, and important examples are quantum Hall effect, topological insulators, semimetals, and often in condensed matter, the reciprocal momenta is the parameter of choice, but this is not always the case, as we saw in one earlier talk by Professor Carpentier. So here I show the familiar Dirac cones on the honeycomb lattice. And so this is a very familiar example of, let's say, a topological semimetal. And this geometry of these wave functions has important physical consequences. However, my motivation is from a geometry of wave functions perspective. And so I could ask a naive question, why the Berry phase winding around a Dirac cone is a pi? And in fact, this is how I got started along this line of thinking. And I'll describe you where I've gotten to. So just a quick, so in the next few slides, I'll say some basic stuff, which will be rehashing for many in the audience. But to set the stage, please allow me a few slides. So geometric phase, the basic spirit is captured by this diagram where parallel transport of vectors acquires a phase. And these arrows are of quantum mechanical origin for us, essentially due to the phase differences of the wave functions, but not quite because of the multifold, the more than two-fold, three-fold band property are also important. And in many previous talks also, we have seen these formulas in quantum mechanics. We use these formulas, Berry phase formulas, to compute the topologically invariant aspects of geometry of wave functions. I just wanted to flash it because they're very nice formulas. So here, the parameter will be reciprocal momenta, and this can then allow me to calculate the Berry phase winding around a two-fold degeneracy, and it will answer the question of why a Berry phase winding is pi. But we can even give a formal argument. So this goes as follows. A general two-band Hamiltonian with a point degeneracy has this form. It's just the sum of Pauli matrices. When A equals B equals C equals 0, we have a point two-fold degeneracy. This is nothing but B dot S, in other words, for spin a half. And the Berry phase, when we can use the previous formulas and calculate, it is just the point at half the times of the solid angle subtended by any path on the Bloch sphere. It's 0.5 comes due to the spin a half structure. So, of course, a point degeneracy is exceptional in 2 dimensions. and we need something to get rid of one parameter, so to speak. So we often use symmetries. And when we do that, this solid angle subtended is 2 pi. And due to the half factor, we get a Berry phase of pi. So this is a standard argument. But for my purposes, I can think of it more in an operational or a pictorial way. And I can calculate this Berry phase winding around a degeneracy in a discrete way. So if I do this, this is our Dirac cone Hamiltonian, and I can write down the wave functions, and I can just calculate using this formula. But the pictorial thing is, if I just look at these phase factors of the wave functions, as I go around the degeneracy, they just fan out like this, and these phase differences are what build up, and they give us this pi. So this way of visualizing will help me to understand the system that I am interested in. So to go beyond pi, one thought is one might want to go beyond 2 bands. Of course, we can actually do it if I relax the degeneracy condition. If I have gapped Dirac cones, I can enclose any fraction of pi. But with the degeneracy condition, let me look for 3-band generalizations. And a simple case is this kind of a 3-band generalization. This is again nothing but a B dot S Hamiltonian, but now for a spin 1. And so therefore, now going via the same arguments, the Berry phase of this band structure is 0. And there's a notable example of this case on the lattice, which is called the alpha T3 model by the Orsay group, which actually is quite nice because it allows you to interpolate between spin half structure and spin 1 structure. The lattice lives on a dice lattice, and then you can interpolate between spin 1 and spin half nicely. So with this, I'll come to the Hamiltonian that is of interest to me. So let me consider this kind of a 3-band Hamiltonian. So now you see that we have this extra matrix element. And if I just look at its spectrum, it looks like this. And this is quite striking. And so there is a 3-fold degeneracy at the origin, obviously. But there are also these line degeneracies that sort of come out. They emanate from this 3-fold degeneracy. And so these line degeneracies are crucial. And this already kind of gives me a sense that this is not quite like a Dirac geometry. And my goal is to convey to you how to understand the geometry of this Hamiltonian. And I'll explain how this is, in some sense, beyond Dirac. So to give some context, there has been a lot of attention on 3-fold degeneracies. These are sometimes called triple point fermions, both in 2 dimensions and 3 dimensions. These are definitely an incomplete list of papers on the subject. So this number 19 is the alpha tau 3 model, and people in different communities, band engineering, in photonic insulators, etc., also thinking about these things. But the point is, often they are spin 1 cases. But there is one important notable exception, which is this reference 29. This is in 3D, and this has been termed nexus fermions. So there it has some resemblance to the system of interest that I'm looking at, and I believe that what we have done has some relevance to this 3D system. So this nexus fermions has a certain precursor in this paper. So here they were interested in the band structure of graphitic systems, and you could see line degeneracies connecting different Dirac cones. And so these were 2-band systems, and so this was a 3-band case of that, which was termed nexus fermions. So let me try to understand the geometry of the model Hamiltonian that I wrote down. So reference 29 argued that the band structure, the nexus fermions band structure that they have, is a beyond-while kind of band structure. I'll come back to this point at the end of the talk. It is in this sense that we are going beyond Dirac in this 2D case. And the utility of this model is that I can explicitly see how I'm doing this. And the point is the line degeneracies are important, and this obviously precludes a regular Berry phase calculation. So the first thing that I could do is I could just monitor the arguments or the phases of the entries in the wave functions. So these are the plots of I just look at the arguments of the entries in the wave functions just by setting the third entry to 1. So that's a gauge choice. And I just look at the phases, and I see there's already something interesting happening. The phase doesn't close on itself, there's a sort of discontinuity, and this is happening due to the line degeneracies, not surprisingly. So the geometry is as follows. The three bands are, in a sense, intertwined among each other. And so to see this, you can already see this in this diagram, but if I just make a cut of this at a fixed magnitude of the momentum, it looks like this. And so therefore, to move along in the band structure in a smooth way, I have to just cross across bands, because any loop encircling the point degeneracy will necessarily encounter a line degeneracy. In contrast, I can look at a different three-band model. There's a very slight difference between this and the previous model, just a sign change in the matrix elements. This also gives you this, but here you can stay within one band as you move amongst the bands. And so the main message that you learn through this is that whenever I encounter line degeneracies, I have to analytically move across into the other band. That is the way to move analytically in the space, and that what will govern the geometry. So in this case, this is a comparatively trivial case, but here is the more interesting case. This you can think of it as adiabatically connected to a folded version of the triangular lattice single band. So this toy model, what happens is that you can actually write down the eigensystem itself. This is the eigensystem of the toy Hamiltonian. And so these are the three bands, the eigenenergies and the eigenwave functions, but they are really the same wave function in some sense. And this line degeneracy structure, what it is doing is you note these factors of e to the I 2 theta by 3. So they are non-analytic in the complex plane, and to sort of make sense of them for analytic emitting, I need three Riemann surfaces that we learn in complex analysis. So it's really one single band which is analytically intertwined among each other. That's what's going on. And it is somewhat, you can see it at the level of the spectrum. I can rewrite these functions as just real parts of the three branches of the complex cube root of Z. So this is this toy model helps us to make this explicit. So as I said that these e to the I 2 theta by 3 factors makes the analytic movement explicitly, and that tells me how to move analytically among the bands. So for example, if I start here, then I've fixed the magnitude of the momentum to 1. So I'm just going in a circle around the origin. So if I start here, to come back to itself in the system space, I have the same eigenenergies and the same wave functions. If I start here, I'll encounter the degeneracy, and then I'll cross over to the other band. Then I'll come here, I'll encounter the other degeneracy. Then I'll cross over to the third band, and then I'll go here, and then finally I'll arrive here. So I have to do it 3 times to analytically move in this eigensystem to come back to the same starting point. So this then motivates me to write winding numbers to sort of to spell out the topologically invariant geometric information about the wave function geometry. But as we saw, we can't circuit the threefold degeneracy once. I actually have to circuit the threefold degeneracy thrice. I need 3 circuits, but the interesting thing is when I do these 3 circuits, the wave function actually winds twice. So this is really just this 2 theta by 3, as theta goes from 0 to 6 pi, 2 theta by 3 goes 0 to 4 pi. So this Beyond-Dirac is this relatively this different kind of winding of these two, the parameter and the wave functions. There's a relatively prime way in which they wind, and that is what you can think of as a Beyond-Dirac property of these wave functions. So here we have tabulated several examples. In all the Dirac-like examples, this relative prime property actually does not happen. Rather, you always have a multiple of the other windings, whereas only in this model, it's a relatively prime way of winding in the wave function space. So it is in this sense that this toy model captures a Beyond-Dirac geometry. So, of course, we can ask where could such a thing, such a continuum model come from? And we notice that these are actually just 3 copies of honeycomb hoppings. So you can then put it on the lattice because you want 3 copies of honeycomb hoppings, you need a honeycomb lattice with 3 sites per unit cell. And so this is an explicit construction. In the unit cell, I can put 3 sites. I have 1 extra site on the middle of the bond unit cell. So then I can ask a symmetry question, what kinds of these 3-band Hamiltonians. So I've restricted myself to spinless cases. What kind of 3-band spinless Hamiltonians can arise consistent with the symmetries of this lattice. So the usual argument we make for 2-band honeycomb, where we have inversion, time reversal, and these symmetries to protect Dirac cone degeneracies, because 2-fold degeneracies are otherwise exceptional, we can do the same kind of thing. If we just do that analysis, I'll get the regular Dirac cones for 2-band case. But now I can try to do the same kind of analysis for the 3-band case. So first of all, in this way of writing, I can write this model Hamiltonian H3A in this form. So the point is it involves all of diagonal matrix elements of these Gell-Mann matrices, which are the generators of SU3, whereas this other thing that I had written in the spin 1 case actually just used the spin 1 generators of SU2, not surprisingly. So that is the point. That, from a symmetry point of view, this involves all of diagonal matrices. And then I need to find out, consistent with the symmetries of the lattice that I'm anticipating, what are all the space of Hamiltonians that will come out. So in this case, the symmetries that I keep are C2, time reversal, and the parities, but I don't keep C3 because the diagram that I showed didn't have C3. And so then I can use the standard technology to find out the whole space of Hamiltonians which arise out of this analysis. I actually find it's a big family. It's not surprising in hindsight. And so therefore, I now have to categorize the various kinds of band structures that result from this family. And what you find is that the line degeneracy like Hamiltonians are actually require fine tuning. It is not surprising in hindsight because in 2 dimensions already point degeneracies are exceptional. So having line degeneracies in 2 dimensions is even more exceptional in a bad way. So they require fine tuning. So the most generic case is this case, which actually just reduces to point degeneracies, which is not surprising. If I have enough symmetries in the system, they can be protected by lattice symmetries. But the crucial point is the organization of these Dirac cones is actually deriving from the SU3 structure underlying here. So in the sense that suppose I have the quadratic band touching of bilayer graphene, when I include some extra hoppings, the trigonal warping terms consistent with the lattice symmetries, they split into 4 Dirac cones. It is in that sense this fine-tuned Hamiltonian splits into these 3 Dirac cones. Also, there's a mass term which is allowed by symmetry, which can gap out the Dirac cones in the same sense as gap Dirac cones. So I can put all of this on the lattice, and this is just for completeness. I show that I have all these 3 kinds of hoppings from between the 3 sublattices, and I just have to be symmetry consistent. And if I allow any symmetry allowed hoppings, I get the generic case. But if I fine tune it, then I do get these line degeneracies. One interesting thing on the lattice which happens is that this line degeneracy actually winds on across the Brillouin zone. It's on a non-trivial loop across the Brillouin zone. And on the lattice, there are curvatures induced. So sort of a little interesting fact is that even in this generic case, there's exactly a flat line here connecting these 2 degeneracies in the continuum. When I put this on the lattice, there's a certain curvature to that, but it is still quite flat. So, so what we learn here is that these line degeneracies are not quite generic in 2 dimensions, but what has been shown that in 3 dimensions, such 3-fold degeneracies with 2 line degeneracies coming out can actually be guaranteed by symmetry arguments. And so the details of this argument is given in this paper, and it's a nice argument. Basically, the basic idea is you use two different crystal symmetries which are mutually non-commuting, but they both individually commute with the Hamiltonian. And if they share a common axis, on that axis you can have two different eigenstates with different quantum numbers, and you get the line degeneracy. So that's a neat argument. And so they showed that you have this line degeneracy structure in 3 dimensions, which are protected by there's a specific space group in which you can realize. I've forgotten the exact number. And also they proposed a material realization of this, in particular tungsten carbide. The interesting thing for me is that if I look, so these figures are from their paper. If I look at a cross section of their band structure, it exactly looks like what the toy model that I had written down. So the geometry is it can be understood from what we saw before. And so this is, so they argued how this is beyond while by showing that if you enclose the threefold degeneracy around the threefold degeneracy, any sphere that encloses that degeneracy will always have a gapless point sitting on the sphere because of these line degeneracies. And so therefore you cannot think of it as a while. So as I said, the beyond while was implied because any sphere enclosing the threefold degenerate point encounters a gapless point, and so it is not thinkable as a while system. In our toy model, we also had the same feature / bug for any loop now enclosing the threefold degeneracy. But in spite of this, in this toy model, we can understand the geometry quite well, and I believe that is the main utility of this. And another sort of general message is these gapless points are not a roadblock to understanding the geometry of wave functions. Rather, analytic movement across them governs the geometry of the wave function space, and they become crucial in this particular example where you have line degeneracies always present. And in fact, in the 2D case, we can do a calculation to give a topological invariant way of doing it, and we suspect our 2D understanding can help complete the 3D story. So here, if you notice, they did calculate the Berry phase winding around the line degeneracy. It was 2 pi, but there is no topological invariant written down which captures the full 3D structure of this. But we can already get a sense that if I make cross sections around the line degeneracies, they will just be this, whose geometry we already understand with the toy model. And then if I just keep rotating that circle, because it's graph everywhere, I'm just analytically continued, and I can perhaps build some topological invariant to spell out the topological information of this band structure. That is what we are thinking about right now. That work is not yet finished. Just an aside, the Borofine material does have a lattice, but I couldn't find in literature if these kinds of threefold degeneracies are present in the band structure, even somewhere deep inside, not near the Fermi surface. So I can present this calculation since I have some time. So the point is, since what we realize is that this toy model, the bands are completely intertwined between each other. So you cannot really think of them as 3 separate bands. That's the main point. And so therefore, the adiabatic evolution cannot remain in a single band. It will happen across the 3 bands as I circuit the degeneracy. And so then if I set it up, it gives rise to a non-abelian geometry in the space of these wave functions. And I can then actually evaluate what is called the holonomy of this wave function, of this evolution, using these definitions given by Wilczek and Z. And these are 3x3 matrices. So that's really how you think about this system. It's in a matrix way rather than in an abelian Berry phase way. And you can compute this. It was easier for me to compute it in a discrete way. You just arrive at this. So this is again capturing the same winding number information that we had seen before, that I need to actually circuit thrice to get back to the same starting point in the wave function space. Here, this 3x3 matrix is telling me that when I wind once, if I start in the first band, I end up in the second band. If I start in the second band, I went up in the third band, and so on. And if I raise this to third power, I will get back identity, which is the 3 times winding that I needed. So with that, I come to my conclusions. So the details are in this paper, except for this non-abelian part. So we saw a toy model way of understanding these of what can be called Beyond-Dirac fermions. And the utility of this model is that I can make the geometry of these wave functions explicit. And we believe that this is pertinent to understanding the 3D nexus fermions. In particular, how to spell out the topologically invariant information of this band structure. And a speculation can be made that perhaps these 2D nexus fermions also, if they can be somehow protected on the surface of some 3D system, but that is pure speculation. And further topics are to understand. So this was mostly motivated by wave function geometry, but one can of course ask what are the physical properties of these wave functions and also the effect of interactions. With that, I acknowledge my funding sources and few discussions, and thank you for your attention.
Thank you, Sumiran. Questions?
You show some table. Couldn't quite follow, so
Sorry.
Explain a bit more about that. Theta p and h. Yeah, so theta p is the winding number.
Theta p is the parameter winding around the point degeneracy. So if I so given p, I can define the angle in the p dimension. So that's the theta p.
That's let's say 3 times 2 pi.
Yes.
Maybe you should have written theta p over 2 pi or something.
So I have to wind 3 times around the circuit is what I mean.
In the figure, you plot the pi 2 pi. So theta p is angle. So the table theta p is in. I guess you mean.
I mean I have to wind thrice. Yes.
What is h?
H is the Hamiltonian. So I just look.
Oh, you
the matrix elements.
H1, H2.
These matrix elements, how they wind. Yeah.
Thank you.
Yeah. So actually, I can make a comment here. So from a model building perspective, you could have asked, say I have a two-fold Hamiltonian, I can just reverse engineer any geometry that I wanted. So I could write any two-fold Hamiltonian like this. I can just reverse engineer the geometry that I want. But then what you will find that if you want to go beyond pi, if you just write down this matrix out, you will find that the matrix elements won't be analytic. And we want them to be analytic because we want them to come from some lattice model. And it is in this model, interestingly, you see the non-analyticity in the eigenvalues and the eigenfunctions. In this sense, I will have a third term. They will cancel out to give you analytic matrix elements.
You mentioned about Borofin.
Yeah.
Recently, my collaborator Akbar Jafari has looked at Borofin, and he focused on the tilted nature of the Dirac cone, which he finds as like an analog gravity, some event horizon. May like to look at it. Okay. Another comment I wanted to make is I was reminded of a very early work by Walter Kohn. What he does is he takes a periodic potential in one dimension, solves a problem analytically, and analytically continues in the wave vector k. Then by that he is able to go through every band. So you are crossing, go around, go from first band to second. So the entire spectrum is generated from a single.
But with gaps between the bands? Or with...
I don't remember. So it's a special.
Okay.
You can give it.
Okay, please. Yeah.
More questions?
So, as I have remembered, means just like in the single layer graphene, the topological winding number is 1. In bilayer graphene, topological winding number is 2. And if you measure the Hall conductivity in single layer or bilayer, so near the charge neutrality point, the gap between two plateaus scales like if the topological winding number is 1 or 2. So just like in single layer, you will get 4 square h gap. In bilayer, you will get 8 square h. So is there any possibility that in your model, since the topological winding number is 3, so if someone calculate the Hall conductivity, what will be the gap between this plateau near the?
So if I look at the generic case, you have these 3 Dirac cones, and so they have their own, they have the usual Dirac cone winding. Now if you put in a magnetic field and form Landau levels, they will have their own splitting. And so maybe here you can have a multiplicity of that sort, because I have 2 Dirac cones and this is spinless right now, but here you will get like a regular Dirac cone. So there will be actually a change in that sense.
One question means in your presentation you have written that the gap Dirac cones can have any fraction of the pi.
Yeah.
So can someone think means intuitively how it happens?
I mean, all I just mean is that once I have a third parameter, I can enclose any area on the block sphere that I wanted.
Okay.
So that's all I meant.
Any more question? Not. Let's thank Sumiran once more.
Thank you.